Hello everyone, welcome back to the AI Tools Research Channel. I'm your host, Zeb Batty. Today we'll be discussing an extremely exciting topic: artificial intelligence and quantum supremacy. We'll be covering the promises and risks of the convergence of these two very powerful technologies. This video is in two parts. In the first part, we'll explain quantum computers and how they are different from present-day classical computers. In part two, we'll cover the challenge in building quantum computers, the various algorithms, the potential marriage of AI and quantum computing, and the promise and risks associated with this powerful union. So let's first begin with how classical computers work. Classical computers are made possible by something that is similar to a light switch. A standard light switch simply turns a light either on or off. This can be translated as a yes or no, true or false, etc. The brain of a computer, something we call a CPU or central processing unit, is made up of essentially billions of light switch-like components called transistors. A transistor is simply a device that either has a current flowing through it or not. When a current is flowing, it is on, or true, or equivalent to a 1. When no current is flowing, it is off, or false, or equivalent to a 0. This is what binary means, either a 1 or 0. A standard computer only understands this binary language. What is a 1 and what is a 2? So the question is, how does a simple device like a transistor make complex and sophisticated computers? To answer this, let's look at the inside of a classical computer's CPU and see how it actually works. First, for any computer to work, it needs a power source, because energy is needed to run the system. For this, all computers need a power supply. Second, a computer works with a lot of data, so it needs a place to store and retrieve the stored data. For storage of large amounts of data, hard drives are used. But bulk storage devices are simply too slow for the speeds needed to transfer data to and from the CPU. To solve this problem, computers have another storage facility called RAM, or random access memory. RAM is a much faster storage device than any hard disk, and it physically located closer to the processor, allowing higher bandwidth and faster flow of data. But RAM is also a temporary storage device, just there to facilitate the CPU to store immediately needed stuff. When you turn the power of computer off, all working data stored in the RAM goes away. All these devices, power supply, hard drive, RAM, etc., are really there just to provide support to the primary activities and operation of the brain of the computer, which is the central processing unit, or CPU. The CPU does the actual computation and decisions. As stated earlier, a classical CPU is made from transistors, and a transistor is basically like an on and off switch. If it is on, then it's considered as 1. And if it is off, it's the number 0. Groups of transistors connected in the appropriate way form what we call logic gates. These logic gates inside the CPU do the actual computation. To understand how logic gates work, let's look more closely inside the very first available general-purpose CPU, which was introduced by Intel Corporation in 1971, called the Intel 4004. By looking at this relatively simple processor, we will get an idea of the architecture of a CPU. The Intel 4004 was a 4-bit processor. This means it can work with inputs formed by 4 bits. Thus, the processor could accept an input like 1, 0, 1, 1, which is also called a word. A word is group made from 1s and 0s with which the CPU works. And in the case of the Intel 4004, it uses 4-bit words and consists of two 250 transistors or two 250 switches. To give you an idea of how much Intel Corporation has progressed in 50 years, their modern processors are 64-bit processors and consist of billions of transistors. Now let us look closer at how a computer actually works by processing just 1s and 0s. The internal diagram of the Intel 4004 chip looks like this. There are some timing controls at the bottom responsible for keeping the operation synchronized, because if not synchronized, the computer will get lost with what it's trying to do and crash. There are some registers and an address stack for storing values to keep track of the data that the processor is working with. It also has an instruction decoder that helps decipher the code and figure out what the CPU should be processing. And we have some I/O or input-output to communicate with the other components of the computer. The magic all happens at the ALU, the arithmetic logic unit. This is where everything is calculated and processed. The rest is mostly just data management and data storage, so it's really not that complicated. Basically, you take some input, perform a set of operations on it, and then you get an output. The end result is a set of output data. There are many more components needed to make all this synchronized and smooth, but essentially that's it. Now that you know about bits and how the classical computer works, let's see how the quantum computer works. We know that in a classical computer, we have electrical signals that flow through a circuit. If there is a signal, you have the 1 state. If there is no signal, you have the 0 state. Thus, each bit in a classical computer can only be in one of the 2 states. So, if you have 2 bits, you can see that the maximum combinations these 2 bits can give is 4. You can write these values as 0, 0, 0, 1, 1, 0, and 1, 1. These are 4 numbers. To determine which one of the 4 numbers we have in the computer code, you need to know the value of the first bit and the value of the second bit. Now, how do quantum computers differ? Well, quantum computers in principle do the same computations as a classical computer. But instead of bits, the quantum processor uses qubits or quantum bits for the computations. What are qubits? Let's explain them. And for that, we need to delve into the world of fundamental particles and quantum objects. The term quantum objects means that these objects belong to the mysterious world of tiny fundamental particle ruled by uncertainty and probability. This is the world of the smallest particles that make up all the matter in our universe. That is you, me, plants, animals, planets, galaxies, literally everything. The properties of these particles are called quantum properties, which include superposition, entanglement, and spin. Qubits can be made with one of many quantum objects, like electrons, photons, and atomic nuclei, etc., that have some binary property like spin. It would be unfair to move on to quantum computing without explaining this concept, because this is at the heart of quantum computing. Spin is a quantum mechanical property of particles that is analogous to angular momentum in classical physics. However, unlike classical spinning objects, quantum spin doesn't involve actual spinning. Instead, it's an intrinsic property of particles like charge or mass. Particles like electrons, protons, and photons have this property called spin, which can be thought of as a kind of internal angular momentum. Spin states, especially of electrons, and nuclei, like in phosphorus atoms, are often used to represent qubits. The spin can be in an up state, often represented as 1, a down state, 0, or in a superposition of up and down states at the same time. Understanding the interaction of superposition and spin in quantum computing is important. The superposition principle allows for the representation of multiple states simultaneously. When using spin as the basis for qubits, this means that a qubit can be in a superposition of both spin-up and spin-down states. To understand this further, if you are confused, imagine flipping a coin in the air. When the lands, it is either a head or a tail, but when the coin is in the air, it is spinning, so it is both heads and tails at the same time. We call this superposition, or being in both states at the same time. We only know which if it's a head or a tail when it lands and is stationary. Qubits behave in a similar manner as a tossed coin. They are bits that are in a superposition of both 0 and 1 at the same time, so they can potentially take on an infinite number of values between 0 and 1. When a quantum system in superposition is measured, for instance a spin-based qubit, it collapses into one of the possible states, either spin-up or spin-down in this case. It is like when a tossed coin lands on the ground, it can only be in one position, heads or tails, and not both. Superposition and spin are crucial concepts in quantum computing. Superposition is about the ability of quantum systems to be in multiple states at once, and spin refers to an intrinsic property of particles that can be used to encode quantum information. Here are some of the key types of particles and systems used to make qubits. Photons. Photons, or particles of light, can be used as qubits. Their quantum states, such as polarization, can represent the zeros and ones of quantum information. Electrons. The spin states of electrons, up or down, can serve as qubits. Electron spins in materials like silicon or diamond are commonly used in quantum computing. Atomic nuclei. Certain isotopes have nuclear spins that can be manipulated to create qubits. Techniques like nuclear magnetic resonance, NMR, are used to control these nuclear spins. Superconducting circuits. These involve electrical circuits containing elements like Josephson junctions. They operate at extremely low temperatures and can represent qubits through different energy levels. Trapped ions. Ions, or charged atoms, are trapped using electromagnetic fields, and their internal states or motion states are used as qubits. Laser pulses are often used to manipulate these ions. You can see that qubits, being in superposition, has significant advantages over classical bits. While classical bit can only be in 2 states, which is 0 or 1, qubits can be in a state of both 0 and 1 at the same time. and qubits can store 2 to the power of the equivalent number of bits. 3 qubits can hold 8 classical bits, and so on. Quantum mechanics allows us to make superposition of each one of these 4 states of the qubits. So we can write a quantum mechanical statement, which is some coefficient times the first value, plus some coefficient times the second value, plus some coefficient times third, and so on. Now let's review this concept again. So to determine the state of this 2-spin system, we need 4 numbers, 4 coefficients, whereas in the classical example of the 2 bits, we only need 2 bits. And this is how you understand why 2 qubits actually contain 4 bits of information. We need to know 4 numbers to tell the state of this system, whereas in classical computers, we only need 2. Now, if we have 3 qubits, we would have 8 different states. We need to know 8 different numbers to define the state of those qubits, whereas classical is just 3 bits. With 10 qubits, we would be able to store the same data as 210 or 1024 classical bits. If you keep going, what you'll find is that the amount of equivalent classical information contained by n qubits is 2 to the power in classical bits. And of course, the power of exponentials tells you that once you have, let's say, 300 of those qubits in what we call the fully entangled state, you are able to create these really crazy states where there is a superposition of all 300 qubits in different states. By the way, 2 to the 300 classical bits is as many particles as there are in the universe. So far, we have established that qubits are quite different physically compared to the bits of a classical computer. We know that in a classical computer, we use electrical signals that flow through a circuit. If there is a signal, you have the 1 state. If there is no signal, you have the 0 state. The qubit, on the other hand, is usually stationary. It's located in a physical place on the quantum chip. So they do not flow like classical bits through a gate. A gate is a basic electronic circuit that performs a logical operation on 1 or 2 input bits and produces 1 output bit. But how is the gate applied onto the stationary qubits in quantum computing? Well, this is done using photons, in particular using microwave pulses. But the exact detail depends on the design of a specific chip. If we have 2 qubits in a circuit, instead of adding just 2 numbers together, we could potentially do 4 additions at the same time. If we have 3 qubits, we could do 8 additions at once, and so on. Adding 2 numbers on a quantum computer isn't any better than on a classical computer. But breaking a 10-digit combination of a lock is another story. Let's explain how classical and quantum computers will tackle this problem. First, we'll explain the classical computer approach. A regular computer, like the one you might have at home, would try to find the magic combination by checking each possible combination one by one. Since there are 10 numbers in the combination, there are 210 or 1024 possible combinations to check. That's a lot of combinations for the computer to try. Now let's explain the quantum computer approach. We'll use 10 qubits for our example. So our quantum computer has 10 qubits, 1 for each number in the combination. Each qubit can be in a state that represents both open and closed simultaneously. This is a bit like the quantum version of being both heads and tails at the same time. This means the quantum computer can look at many different combinations of open and closed positions all at once. With its quantum magic, the computer finds the right combination much faster than the regular computer. To summarize the above example, the magic number represents different possibilities that the quantum computer can explore simultaneously, thanks to its 10 qubits. While a classical computer checks each possibility one at a time, the quantum computer uses its qubits to explore many possibilities at once, finding the solution instantly. This is a simple way to understand how a quantum computer with 10 qubits can solve certain types of problems more efficiently than a regular computer. This brings us to one question that is frequently asked. Is the quantum computer faster than the classical computers? The answer is not always. One thing that quantum computer scientists agree on is that a quantum computer won't solve every type of problem. It is well suited for only certain kinds of challenges, like probability problems, optimization, like finding the best possible travel route, or needle in a haystack type of problems, if you just want to watch a video in high definition, or browse the internet, or write some document in Word. Quantum computers are not going to give you any particular improvement over classical computers. Quantum computers should not be seen as universally faster for every operation. In fact, most operations might be slower than those on your desktop computer. Quantum computers are not outright replacements for classical computers. They excel in particular calculations where quantum superpositions can be utilized for computational parallelism, rather than being universally faster across all tasks. One last point before we conclude this video. Quantum computers are not mature as yet, in part due to the many challenges that quantum computing faces. In part 2 of this video, we will cover the challenges, possible solutions, and the promises and threats posed by the convergence of quantum computers and AI. Thanks for watching. Please subscribe to our channel if you enjoyed this video, and don't miss to press the like button.